Let me. Okay, so welcome all to the second part of the session on non-Archimedean analysis. The first talk today is by Hoai An from the Institute of Mathematics in Vietnam, and the title of her talk is Non-Archimedean Second Main Theorems and Applications. Please start.
Okay, at first I would like to thank the organizer to invite me to give a talk here. Especially thank to Alain Escalcier, Gadindo, and Professor Sam Sedin to set up very suitable time for me. Now it's at 9 p.m. in Vietnam, so I'm very lucky not the last talk. So, okay. Today I will introduce you about non-Archimedean second main theorems and application. First, because some people here are not familiar with never linear theory, so I will introduce a little bit about notation and history. Everyone knows if F is a polynomial over algebraic closed field of degree n, then we know that exactly solution when F hit to any point. But what happens when F is not only polynomial but the entire function? So the situation is not so simple like that. For example, we can look at exponent exponent functions. When it hit to 0, it's no solution. But when it hit to another point, there are many solutions. So never linear theory will tell you how to control about that situation. And then what is the application about that? Okay. At first, I will give some definition. For simple way, I will give definition in high dimensions first. So let F is a non-constant analytic curve into projective space with reduced representative is the F0 until Fn. That means Fi are entire and then have no common zero, and at least one of them are non-constant. And then we take maximum of absolute value, and then take log, and also then take integer, and that makes us a never linear characteristic function with well-defined. And then the second function of never linear theory is called proximity function, corresponding to a homogeneous polynomial Q of degree D. Just take log plus this rational equation, and then we take integer. And counting function is a count how many zero of Q when contact to RF, and we count also with multiplicity inside of this radar R, and then from all of them we can define the effect of F respect to Q by take limited of this formula, and very easy to see the defect of F always bigger than or equal to 0, and also lesser than or equal to 1. But the question is how if we add all of them together, if we can find the bound. So that is the question. And related to what we used to call second main theorem. So how to find the better bound of when we take some of them. And then the second question is, if we know two non-constant meromorphic functions which have the same inverse image of element or set, then when they are equal, or at least we can find some relationship between them. And this problem usually to call problem of uniqueness. So you can see if we know we have one polynomial, so we only need to know image set of only one point. So what happens when we consider for meromorphic function? So Nevalina theory says that if we know image of 5 distant points, then we can see it's determines uniqueness. Related to the question 1, when we consider for n equal 1, that means when we consider the function meromorphic function, then the bounded is by 2, and even that we can add some other term. This makes you you don't need to call all of multiplicity. You only need to see at simple 0. So this is a very strong bounded and the best thing for complex number. So here Ri is a complex number. So the question is, if we consider Ri not only the number but the small functions, what happens? So what bounded we can expect? So f is a meromorphic function and phi is a small function with f if the characteristic function of alpha is a very small compared with characteristic of f. And then Steinmetz and Osgood that prove that for meromorphic function and alpha I are small functions, then the bounded is 2. And you can see here, they only consider for delta f, but in the case of complex number, here, in the case of complex number, the stronger result is can add something more, which then can ignore multiplicity. So recently, Iamanoy, with very intelligent method, he can improve the bounded for ignoring multiplicity. So the question is if we can get something similar for p-Adics case. Unfortunately, we can't. But I will introduce a little bit what we can get here. Oh, sorry. Okay, so I will talk all for complex case first, and then I will tell about p-Adics case later. So you can have better organized about the talk. So in the case n bigger than 2, the Cartan theorem says that the bounded will be n plus 1, where n is the dimension of projective space. And H1, HQ here related to complex number by hyperplane such that it's a linear independence. So linear independent means when you cut down, so the dimension will be reduced 1 by 1 after one time to cut down. So you can see here, Cartan only consider for H1 to HQ are hyperplane. So the question is how we can improve for hypersurfaces. So that is a Shipman result. He considered when D1, DQ are hypersurfaces in general position, and F, even from CM to PN, such that M of F is not contained to any one of hypersurfaces, and then the bounded is a 2n. Of course, it's not so good. And then here, general position means when similar in the hypersurface case, when we cut down one by one, then dimension will reduce until empty after 1 plus time. So and the best result now given by Minju for F is a projective is an analytic curve into projective space. Then the bounded here so can get n plus 1. And remark that the rule result need algebraic non-degenerate, and also not clear that this result can improve Eremenko-Sodin result or not, because in Eremenko-Sodin result they only need M of F is not contained to anyone. So two of them are independent. Even Zhu result get better bound, but the condition of Ru result and Eremenko-Sodin result are, we don't know if related or not. So there one conjecture which given by the Griffith. He say that if D1, DQ are hypersurface of degree D, of course we can take all of them are different degree, and after one time change degree, we can assume that they have the same degree, and they stay in this general position with Pn, and then the boundary should be n plus 1 divided by the degree of hypersurfaces. This is a very strong result. Until now it's still open, but remember that F have to be algebraically non-degenerate in Pn. If we reduce this condition into one variety, then the condition is not correct. And here is one example. That means we can take in P2 and Di are conic, no more crossing. No more crossing means they don't have common tangents. Then the boundary will given by 7/2. Yeah, that is for complex case. So for Nevalina theory, if we have something in complex case, we will expect something in p-Adic case. So what will happen in p-Adic case? I will introduce to you. So here we consider K is algebraically closed field with any characteristic complex with non-Archimedean absolute values. And A is an entire function and expand by this. And then we can take value of A over this R. And then like what Alain and Professor Sambersedin said yesterday about norm of non-Archimedean, and then this only can take sub over, no need to take all inside the disk. We only need to take in circle, on circle, okay? So similar to the complex case, we also define the characteristic function, proximity function, and also counting zero function. And for counting zero function is exactly the same with the complex K. For characteristic function, it's a little bit different only because of, the norm here is different. Okay. And then in the case of n is 1, that means f is a meromorphic function. Then what we get for bounded here is a q minus 1 replaced to q minus 2 in complex K. And when the zero don't ignore multiplicity, then the number we get here exactly the same with complex K, only we add some smaller term in the right side. And then therefore the bounded of defect function, the sum of defect function is smaller than 1. And similar to the complex K, the question is if we can change Ri is the constant to be small functions, and what will happen? So remember for Yamanoy K, he can get exactly the same with complex number, but in the case of p-Adics, we don't get that. And what we can get here, so this is the result I work with my student, and he also here today, and he's a Nguyễn Việt Phương. He is here today, and he will defend his thesis soon. So what we can get here, if f is a non-constant meromorphic function over a non-Archimedean field, and a1, aq are distinct small functions respect to f, and then we have the bounded is by 2q of here replaced by 2q over 5. So remember for Ri is the p-Adics number, then here is a q minus 1 or q minus 2. So this is a little bit a lot smaller here. And from this, so in the linear theory, whenever you have second main theorem, this is the second main theorem, then we will have application that we can find about uniqueness problem. What is the uniqueness problem? So we consider E, A, K, F. Here F is a meromorphic function, K is an integer, and A is the p-Adics number. And then we consider the zero of F minus A with multiplicity at mode K. So here we don't need to count all of zero. We only to take the zero such that the multiplicity at mode K. So when K is infinity, so we take all of zero of F minus A equal to 0. And then when A is infinity, that means we consider here is a pole, okay? And the question is, if we have two meromorphic, non-constant meromorphic function F and J, and share point, ignore multiplicity, that means E bar AF equal to E bar AJ. So what we can say about F and J? So the result here we can get that if F and J are the two meromorphic functions and AI are small function respect to F, and J is also small function respect to J, and Ki are positive integer, satisfy this inequation, And then if they share AI with multiplicity counted to kj, then f equal to j. So it looks very messy here. So I will take some special case so you can see how it looks like. Okay, so consider k1 equal to kq, or multiplicity are cut down to the same, and then we only need k bigger than 3q plus 4 over 2q minus 4, and then if the two functions have the same imager with counting until k, then they have to equal. And as a corollary, then we can see if phi is a phi distance small function, then if f and j share ri, ignore multiplicity, then f have to be equal to j. And this is a improved align result we keep yesterday, but actually what we get for this result all come from Alan idea. So I would like to thank to Alan to send us his manuscript and very nice and very well written, so we can get very easy idea from that. And what is the idea from Alan? What I can get here? So in Alan paper, he divide AQ into small set with 3 functions each. So in here, we divide the set into the small set with 5 functions. So for Alan K, when he divide by 3 small functions, he don't need to do anything because I only need to use the mobile transformation. Then he can transfer all of small function into constant, and then can apply second main theorem. But we want to improve a little bit, so we replace to divide by 3 functions, we divide by 5 functions, and then we need to do quite a lot here to get similar what Alan get here. But all of idea come from Alan paper. And then after we have this, so we can see with 5 functions, we have one in equation. So what happens when we have Q? So when we have Q function, so of course we need to divide Q function into a small set, which set have 5 functions, and then we can apply the lemma. And how many sets we can organize? That is a Q take 5, and then we add all of them together. So after add all of them together, we have in the left hand side, we have 2 Q choose 5, and then in the right hand side, what happened in the right hand side? In the right hand side here, for one index ij, then we can see it's appear only Q minus 1 to 4 times. So in the right hand side, we can review a little bit here. So this also exactly what Alan do in Alan paper. He take Q choose 3, but and then in here he have Q minus 1 to 2. So everything here come from Alan paper. So we would like to thank to Alan for very nice method, and we only improve a little bit to get better result. So after that, we can conclude our second main theorem with ignoring multiplicity, and then can get the corollary. Okay. So we also come to higher dimension. So in the complex case, we also consider for f is a meromorphic function, and then can consider for f is a curve, and similar here. We already consider for meromorphic function, so now we go to what happens when f is a curve. So at first we also consider f is an analytic curve into a projective space first, and then the first result related to this is given by Hoai and Hoai is my advisor, my PhD advisor, and Alan know him very well. And the bounded with he get here is also n plus 1. N is a dimension of projective space. And then in 2001, rule can reduce the number into n, what we expect about, but also here we don't get any related to ignore multiplicity. We have to count all of multiplicity. Yeah, so remember here, f is an analytic curve into projective space. So I improve into any variety of dimension n, and then I also can get the bounded by n. And the proof is very simple. So this is the general rule result from projective space to any projective variety. And especially here, K, we can consider for the field of any characteristic, not only for characteristic 0. And then even more better, we can also prove only at most n hypersurfaces such that the defect is bigger than 0. Most of them have to be 0. Only at most n are bigger than 0. Then by this result, we can say that if we take more than n plus 1 hypersurfaces in general position, then any f from k into x omit to bigger than n plus 1 hypersurfaces have to be constant. And this space we call Brody hyperbolic space. That means the space any holomorphic curve into have to be constant. Then the question is when a variety is a Brody hyperbolic. This is also very big problem, and also can work for complex case, also for p-Adics case. So first I will introduce for complex case first. So a manifold X over algebraic closed complex field F said to be hyperbolic if every analytic map from F into X have to be constant. So what we the corollary is one example of hyperbolicity. And one conjecture says that in complex case, the complement of generic hypersurfaces in projective space with degree at least 2n plus 1 have to be hyperbolic. So that means many should be hyperbolic if degree of them are big enough. And this is a very hard problem and also attracted to many mathematicians. For example, Green proved that Pn omit 2n plus 1 hyperplane in general position have to be hyperbolic. And then Eremenko-Sodin and independent by rule also improve hyperplane into hypersurfaces in general position. And here so can get omit 2n plus 1 is enough. And after that, people try to reduce the number here. So they expect like a 2n plus 1 or even little bit bigger. Then they try, for example, they only consider for n is a 2, and they can prove for 4, that means for 2n. And also for 3 components, but degree have to be a little bit bigger. So here, if I have 4 components, we don't need condition about degree. But if we reduce 1 component less, then we have to add condition for degree. So that is what have been done for complex case, and you can see it's not so much. The question is what we can translate from complex case into non-Archimedean case. Then in this case, I get some result. So at first, I want to say about rule result first, and rule say projective space of mid n plus 1 hypersurfaces in general position have to be hyperbolic. And then I improve into any variety. Also, of mid n plus 1 hypersurface in general position have to be hyperbolic. And the question is here. So now we want to reduce the number here, n plus 1 into smaller. So now we don't want to be 1 plus 1, n plus 1. We want to less than or equal at most to n. So what will happen? And we expect that if the degree, the sum of degree bigger than 2n, then they should be hyperbolic. So it's very similar to the Griffith conjecture for complex case, and we translate into non-Archimedean case. So the result we get with Julie Wang and Professor Peterman Wang, Alan know very well. We met each other in Vietnam, and very sorry he already passed away some years ago. And then what we can get here, we can when we reduce the number into less than when we consider for each is any projective space, and each time when we cut down, and then coordinate will reduce 1 time. And if we take cut down enough, that means we cut down n plus 1, then this have to be constant. That means the space have to be hyperbolic. And this result is a sharp. That means if we can, we reduce the number into n, and the degree, one of them are, all of them are 1, then the result is not correct. So that's why when we say about question, if reduce the number of hypersurfaces, then the degree we need to increasing a little bit. So the point to prove this, only use this lemma, and then this lemma says that any irreducible projective curve into over non-Archimedean field of mid 2 point have to be hyperbolic. So this is a very strong result we can use to prove almost everything here, because we our method is we reduce step by step until to curve, and then when we can get to curve, and then we can use this lemma. So what is the one we can get here? At first we get for projective space first. So if D1 and D until Dn is intersect transversely, then intersect transversely means when you cut down and then the tangent space, they don't have common that tangent space. That means after you cut down one time, the tangent space will reduce until only one cut into other that point only. So, for example, if this is not intersect transversely, this is not, but this is. So here is not intersect transversely, but here is a intersect transversely. So if we consider D1 to Dn non-singular hypersurfaces into projective space intersecting transversely, then we can reduce the number from n plus 1 into n here. And then the condition we need here, all of degree of hypersurface have to be bigger than or equal to 2. So the example to show you, if we take one of them have degree 1, then the theorem is not correct anymore. So here's the example. We take D1 is the line, and then DI are quadratic. So we can find there one map from K into Pn omit the n hypersurfaces, but not constant at all. This is not constant. So we take F is 1 z, and of course this is not constant, and come to Pn omit to those hypersurfaces. So reduce from n plus 1 to n, we need to add the condition on the degree from any degree into degree have to be bigger than or equal to 2. And unfortunately, we don't get any more better here. Of course, we don't get, the question is, for example, now we don't omit n anymore. We want to omit less than, like n minus 1, what happened? So the question for general case, we still cannot do. But in some special case, for example, when n is a 2, that means we consider for projective space of degree 2, then we almost can get everything. So here, what we get here, so if D1, D2 are non-singular projective curve into P2, and they intersect transversely without loss of general, we can assume the degree of D1 less than or equal to degree of D2, then P2 omit to hyper surfaces is a hyperbolic if only if they have to satisfy this equation about degree. So either they all have degree bigger than or equal to, or if at least one of them have degree 1, then another have to have degree bigger than or equal to 3, and also the intersection of D1 with D2 cannot have any maximum inflection point. What is the maximum inflection point? Maximum inflection point means, so now D1 is a line and D2 is a curve of degree bigger than or equal to 3. So if the line go through to the curve, not in maximum inflection point. Maximum inflection point means the multiplicity of tangent line at this point has to be 3. So this is the result what we can get the satisfy and necessary and sufficient condition, and then how to prove this? To prove this, it's in fact not so difficult. We only consider separated k by k, and then use the lemma I introduced at beginning, and then we can get everything. Yeah, and finally, for D1 and D2 are generic curve in P2, and if degree, sum of degree bigger than or equal to 4, then we also can get the complement is a hyperbolic. Yeah, this is the end of my talk, and thank you for listening.
Okay, thank you, Ta. Any questions or comments? I think Alain.
Alain need to unmute first.
Yeah, Alain, you are on mute. I think you're trying to say something.
Alain need to unmute first.
You have to turn on your audio, Alain.
Okay.
Yeah.
Do you hear me? Okay.
Well, do you hear?
Yes. So I have just a question to Anne. Concerning the main theorem, the theorem applies to meromorphic functions in the whole field, and since the term minus log of r never appears, I suspect that the theorem, the proof, also works for unbounded functions inside a disk, and probably also out of a hole. What do you think, Anne?
Actually, in the theorem we use to prove the result for the k n is equal to 1. That means for the k meromorphic function share small function here.
Yes.
Wait a little bit, I can show you.
Please, did you ask me a question? I have not.
Yeah, I understand. Yeah, I understand what you want to say. Okay, so to prove this, we have to use second main theorem with in terms of log minus log r.
Yes.
On another side. So if have that term, maybe we cannot get for unbounded function also in the disk, but maybe we also can omit that second main theorem, but use a q minus 1 in the right side, in the left hand side, and then can ignore minus log r in the right hand side. Then what you want to get, maybe can get. But right now, I also use a minus log R here.
Well, there is no log of R minus log of R in the capital S of small r and f. So probably it should work again if you consider meromorphic functions in a disk where either at least the numerator or the denominator is not bounded. Okay, so what I call unbounded meromorphic functions.
Yeah, I understand that. So
Yes.
we maybe can work for that too. We can discuss about that. Because here we don't need use the minus log R inside.
So
the things you want to do maybe can work.
Yes, I think it should work. Yes.
Yeah.
Okay. Any other questions?
The method is very good anyway. That's all for me.
From the method. Actually, from the method, we only improve how to divide the set Q element into pi element. Nothing new here. We get from the idea.
Thanks very much.
All right. Any other questions? Or comments? Okay, so in that case, let's thank the speaker again. Thank you, Ta.
Yeah, thank you very much. And I wish everyone will be healthy, succeed, and especially stay away from COVID.